Right, so let's get started with some standard vocabulary for the statistician. The first one being population. A set, I've said units or individuals. You can imagine people if you wish, but it doesn't have to be. It could be households, it could be nations, it could be cars, it could be widgets. A collection of units. At this point, it is a good idea for you to imagine this as a large collection, lots and lots of them. So, for example, the collection of all households in the United States, millions of them. And associated with this population is a number called a parameter. It is a number which you can calculate from the population. So, for example, if I had every household in the United States and I could go and talk to them, I could calculate the parameter, which is their average annual income. So you can imagine each member of the population holding a ticket, and on the ticket is a number, and the parameter is something computed based on those numbers. It is a single number connected with the population, and it's a number that you're interested in. So perhaps I'm interested in the average annual income of my households in the population. Okay, so how do I go about finding it? Well, I go to every household and I say, what was your annual income? And then I go and do an average of a very long list of numbers. But I can't do that. I don't have the time, and especially I don't have the money. So what do I do? Well, I hope that if I go to a sample, which is a subset of the population, then I can look at the relevant numbers in the sample and make a conclusion about the population. In other words, I can use the sample to get an estimate of the parameter. So think of the population as all US households, then the sample is some small set of US households that I can get myself to. I'm trying to estimate a parameter which is the average annual income of all US households, and somehow I want to get an estimate of that number from my sample. Is this doable? Sure. I can go down the Forbes 1000 richest people in the United States list, and I can take a nice big sample of the 500 richest households in the United States and take the average of their income. The 500 richest households will indeed be a sample. The average income of those households will indeed be an estimate of the average income of all US households. But the reason you are wanting to scream at me is that it will be a lousy estimate. And we've come across this over and over and over again. You want to estimate? Feel free. Estimate anything you want. But not all estimates are as good as others. So how good an estimate is depends on how you chose the sample. And what you're trying to do is you're trying to avoid what is called bias, systematically increasing or decreasing the estimate, sort of moving it away from the parameter because of the way you have decided to choose your sample. So what are good ways to choose samples? Well, people often say you need a nice big sample. Yeah, sure. But other criteria are more important, and nothing makes this clearer than a wonderful example from the 1936 US presidential election right after the Depression, Franklin Roosevelt versus Landon, and it was won, yes, by FDR. And at that time, there was a magazine called the Literary Digest. It's a bit like, Reader's Digest, one of those magazines, weekly. It used to come out and lots of people used to read it. And it was in the business of making predictions, among other things. So it made an election prediction. And at the same time, there was a young person called George Gallup, who was setting up his polling organization. And so what I want to do is compare the two predictions and see which one was better and how it compared to their sample sizes. So the digest prediction was that FDR would get 43% of the vote. By the way, these numbers, depending on how you calculate, whether you're looking at the major party vote or if you are including independent candidates, there are a small number of them. Those may be a little bit off, but by and large, ballpark, these are the numbers to be thinking about. So the digest predicted 43%, which is the wrong answer because FDR won the vote and they're predicting less than half. The independent candidates were had a very small percent of the vote, so they got the answer wrong. Based on what? Based on a massive, great sample of 10 million. That is a huge sample. And so along came George Gallup and he said, I'm going to make this prediction. But he was a little bit mischievous. Not only was he going to predict the election, he was, before the digest made its prediction, he was going to predict what the digest would predict. Now that's fun. So what do you think he predicted they would predict? His prediction of the digest prediction was 44, very, very close, and based on a mere 3,000 votes. So think about that. He would have done just as well as the digest with 3,000 people in the sample as opposed to their 10 million. Already you have a huge saving in resources here, but you know, both of these answers are wrong. And really nobody cares what the digest predicts. What people care about is who is going to win the election. And so Gallup predicted the election result, and his prediction was that Roosevelt would be getting 56% of the vote. At least he's getting the answer right. He's picking the winner. Based on really 50,000, pretty small compared to 10 million. So what was the election result? Well, it was a landslide for FDR. He got 62, and 56 is still quite far away from 62. But it is not as far as 43. This was a massive embarrassment for the digest, and the magazine folded shortly after. And it's well worth examining why this sample size didn't dominate the methods here. And so what was the sample when 10 million, you need to have 10 million names of voters. Well, 1936, where do you get names of voters? We need lists. Who has lists? Clubs, memberships, phone books. 1936, just out of the Depression, nobody had any money. Who had a phone? That's right, rich people, who were by and large voting Republican. Roosevelt was, of course, the Democrat candidate. So these 10 million were already a section of the population which did not include an important section as far as voting behavior went. And moreover, these 10 million, they got sent a questionnaire. What did they do? What do you do when you get sent a questionnaire? Exactly, you toss it, so did they. Of the 10 million, only about 2.4 million responded. Well, that's pretty small as a response rate, and people who respond are very different from people who don't respond. So even though the sample size was ostensibly large, there were two very serious biases, which I'll name in just a moment. Systematically excluding a section of the population and then not getting responses from those who were included. What Gallup did was he knew what they were going to do. He knew what the digest was going to do. He knew what lists they were going to use. So he selected a mere 3,000 names from those lists, but at random. And he went after them. And based on that, he did just fine. He also predicted his 50,000. Using his 50,000, he also predicted the election result. Did very well. These days, a 6% error, we would raise our eyebrows. But, you know, that was the start of something wonderful. And those of you who are from the UK, please Google Gallup and the 1945 UK election. He was one of the very few people who got the answer right there. So what are the biases that we're trying to avoid? Well, many, but two big ones are selection bias. systematically leaving out a section of the population. So if you only use the phone book, then you don't get the people who aren't in the phone book. And non-response bias. People do not answer survey questions, by and large, and when they do, very frequently, it's because they have an axe to grind. They're really, really interested in their in that particular question. So when I take teaching evaluations at the end of term, I'm very careful to try and maximize the response rate. Otherwise, I get two kinds of evaluations. I get the people who think I walk on water, and I get the people who think that I should not be allowed to walk on this earth because I am the embodiment of evil. Not many of those, but there's always one or two. And then there's the vast majority who really, they have final exams and they can't be bothered filling out evaluations. Thank you very much. I need to hear from them. And so ensuring that people answer your questions is very important, and you have to be rather dogged and go after those people, because you can't replace them with other people who have their hands up to raise your to answer your questions. Read your textbook. There are many other kinds of biases, which is all rather, much of it is common sense. You really want to avoid these biases. So how do you avoid biases? We'll come to that in a moment. The point I'm making here is that if your method of sampling has serious biases, then don't take a big sample. You're wasting your time. You just end up with a big bad sample. You're going nowhere. Better off randomize. Allow Tyche, and if you weren't in 2.3, 2.2 or 2.1, you haven't met Tyche yet, Tyche. Meet her, she's the goddess of chance. Allow Tyche to choose your sample and you'll be in good shape. So what is a random sample? Well, random doesn't mean any old sample. It doesn't just mean a sample you can't predict. It has a very precise meaning. If you're calling your sample a random sample, or equivalently a probability sample, then for every member of your population, you have to be able to say, before you draw the sample, the probability that that member is going to get into your sample. Those probabilities don't have to be the same from one person to another, but you have to be able to say what they are. If they are not the same from one person to another, then you're going to have to adjust accordingly when you do your standard error calculations. Here comes Stat2.3x back again. You remember standard errors, the amount of chance error in your estimate. But you have to be able to say what the probability is, and I'll do it in an artificial scenario. So I will have a massive population of 4 people, A, B, C, and D. And I'm going to take a sample of these 4 people. I like A. I'm going to choose A. I'm going to choose A, and then for each of these 3, I'm going to toss a coin. Toss a coin here, here, here. And if B's coin lands heads, B gets in, otherwise not. If C's coin lands heads, C gets in, otherwise not. If D's coin lands heads, D gets in, otherwise not. Is this a random sample? All right, so is this a random sample? How do I answer that question? I have to say, well, what is the chance that A gets in the sample? I think it's 100%. What's the chance that B gets in a sample? That's right, it's a half, and you can write down the probabilities for each of them. And this is what you have to imagine in your head. If you can do this, list all the people in your population, and if there are millions, then you have to be able to list a million, hopefully in some summarized fashion, and you have to be able to write down the probability that each one enters the sample. And that makes a probability sample. It's going to be important to recognize probability samples from other kinds of samples and particular kinds of probability samples from other kinds of probability samples. So let's take a look at types of samples. The one that people love is the first 10 people that pass you. So you're trying to do a survey and you need to get a sample of people. You stand at the side of the road and you take the first 10 people that pass by and you say, well, that's random. I don't know who's going to pass by. I'm not choosing them. It's not random. Even if you can write down what your population is, there is no way you can write down the chance with which each person in that population walks past you at that moment, and therefore you're going to have terrible trouble computing standard errors. So this is called a sample of convenience, It is not a random sample. An old familiar one is the simple random sample. Draws at random without replacement. Definitely a random sample. What is the chance that a particular person gets into the sample? Now first, in this case, it's the same for all people, and it is Memories of Stat2.3x, the hypergeometric lecture. If you have a population of, say, size 1 million, and you're sampling 1,000, what is the chance that any particular person gets into the sample? It's 1,000 out of 1 million. Little n over capital N. Go back and look at the hypergeometric section in Stat2.3x. This is something that actually worked out in a lecture. Straightforward to understand this kind of sampling, straightforward to analyze, well, relatively straightforward to analyze, but actually quite hard to do. If I have to take a simple random sample of UC Berkeley students, UC, University of California, Berkeley students, not so easy. Because what is the first thing I need? I need a list of all approximately 30,000 Berkeley students. I don't have such a list. Nobody's giving me such a list. It is not so easy. If I had that list, then I would number everybody from 1 to 30,000 or so, and then I would run my random number generator, and I can pick as many as I want without replacement. But I don't have that list, so what do? Well, I go around looking for lists. What do I have a list of? Very easily at hand. Every university has this. You know what I have is a list of classes. So something I can do is choose what is called a cluster sample. I can randomly sample classes. That I can do by throwing darts at the class schedule and then take everybody in those classes. That's a perfectly good random sample for any student. You can write down what the chance is that that student gets into the sample. It has to do with how many classes I'm choosing and how many classes that student is in. But while it is a random sample, is it a simple random sample of students? It is not. It is a simple random sample of classes. But if you put together all of the students in those classes, you don't get a simple random sample of students. Many obvious reasons. What's one? Yeah, the same person can get in twice. If I happen to choose 2 of their classes, they can get in twice. If you're chosen in the sample, it is guaranteed that at least one of your entire classes is in the sample as well, which is not at all the case when you're doing a simple random sample. Not everybody has the same chance of getting in. The more classes somebody's in, the more chances they have of getting in the sample. So the cluster sample is indeed a random sample, very frequently done, and you need a little bit more mathematics and a little bit more understanding of the clusters to analyze it. The simple random sample is what we are going to focus on at this introductory level. It has many of the general features of other probability samples, if not the particular calculations. Actually, before I move on, why cluster? Because each class that I select is a cluster of students. You can think of each class as a bunch of grapes. Right? I select this bunch, that bunch, and the other bunch, and then I put together all the grapes in the bunches. The thing to watch out for first is that not everything is a probability sample, and if you're going to do any calculations, you better have a probability sample or a random sample. Not all random samples are the same. Not all random samples are simple random samples. We are going to be in this class focusing on the simple random sample, and very importantly, if you have the formula for one kind of sample, you cannot apply it to another kind because it will not work. Formulas for one kind of random sample might not work for another kind, so before you calculate, please go back and read what was done. Read the words, not just the numbers, to see what the randomization was. And depending on the nature of the randomization, pick your calculation accordingly.